So, good evening and welcome back to this problem solving session for the NPTEL course Geology and Soil Mechanics. So, in the last few weeks, uh, we had solved a few numerical problems regarding permeability in soil, seepage through soil, and construction of flow net, how to calculate the rate of flow, the Hartley gradient, with the help of this constructed flow net, and then the calculation of capillary, the height of capillary fringe, the negative pore water pressure, followed by effective stresses. So, in the specific week, we started learning another uh, important aspect of soil mechanics, that is consolidation. And the fundamental difference between consolidation and compaction is that, so earlier we have learned compaction. So compaction is the densification of soil mass through some mechanical energy by uh, this expulsion of pore air. However, in the case of consolidation, it is the expulsion of pore water. Okay, so this is the fundamental difference. Now, under this heading, consolidation, we learned a few things from this week, like the fundamental aspects or the fundamental concepts of consolidation through spring analogy, how the consolidation parameter or the consolidation can be simulated in the field. For example, laboratory consolidation test through consolidometer. Then the data obtained from this kind of test will uh, will end up with this kind of plot called void ratio pressure plot. And from this plot, you can obtain the compression index, which is very essential, very, very essential to calculate the consolidation which is happening in the field. Then we have learned about a few terminologies like over and normally consolidated clays. Now, the definition of this over and normally consolidated clays depends on the pre-consolidation pressure. So therefore, a fundamental concept of pre-consolidation pressure is essential before classifying the clays as over, either over or normally consolidated clay. So pre-consolidation pressure is the pressure, the maximum past effective pressure to which a soil had been or was subjected in its geological history. So this is called the pre-consolidation pressure. Now, if this pre-consolidation pressure, if the present effective pressure is less than the pre-consolidation pressure, so you can say the clay is over-consolidated soil. That means the pressure which is facing or the soil is facing, that is not the maximum. So in the past, it faced a maximum past effective pressure. That's why the soil is over consolidated. However, if the soil, if the present effective pressure is a maximum pressure the soil is facing in its geological history, then you can say it's a normally consolidated clay. Now, following this discussion, we have learned how to calculate the primary and secondary consolidation settlement of these clays, then the time rate of consolidation through Terjagi's one-day consolidation theory, and the calculation of coefficient of consolidation by logarithmic of time method and square root of time method. So these are the few topics which we have learned particularly regarding this topic consolidation. Now in this week, we will be trying to solve a few problems concerning or we can say up to this primary consolidation settlement. Okay, so regarding time rate of consolidation and coefficient of consolidation, specifically the time rate of consolidation, will devote the next week. So in the next or upcoming session, we'll be solving problems regarding this aspect, the time rate of consolidation. So far in today's session, we'll be solving mainly how to calculate the primary consolidation settlement of a clay. Okay. So with this, we will start today's session. So this is problem number 1 for this session. So in this problem, a stratum of normally consolidated clay 8-meter thick is located at a depth of 10 meter below ground level. The natural moisture content of the clay is 30.5% and its liquid limit is 35%. The specific gravity of the solid particles is 2.65. The water table is located at a depth of 7 meter below the ground surface. A soil is sand above the clay stratum. The submerged unit weight of the sand is 9.5 kilonewton per meter cube and the same weighs 17 kilonewton per meter cube above the water table. The average increase in pressure at the center of the clay stratum is 115 kilonewton per meter square due to the weight of a building that will be constructed on the sand above the clay stratum. Calculate the expected settlement of the structure. So, if we want to draw the soil stratigraphy for this specific problem, so it will be something look like this, that first there will be a sand stratum, this is the sand stratum and this is, sorry, and this is 10-meter thick. Now below the sand layer there is clay. So this is sand and this is clay. Now the water table is located at a depth of 7 meter below the ground surface. So somewhere here the water table is located. Okay, so this is your ZWT minus 7. Now what are the properties of this sand and clay? So the properties of this clay, will write it down first. So the natural moisture content of the clay is 35%. So W equals to 35%. And the liquid limit is given as 35. Sorry, 30.5. That was the natural moisture content, and 35. This is the liquid limit of the clay. And specific gravity of soil solids is given as 2.65. Now coming to the sand, two unit weights are talked about. So first, the submerged unit weight of the sand, which is the applicable for sand, the portion of sand which is below the groundwater table. So gamma submerged, or rather we can say gamma prime, it's given as 9.5 kilonewton per meter cube. And the bulk unit weight of the sand, this is applicable for the portion of sand which is above the water table. So gamma This is given as 17 kilonewton per meter cube, and this is the ground surface. Okay. Now, in addition to this data, one more information is given to this problem, that is the average increase in pressure at the center of the clay stratum is 115 kilonewton per meter square due to the weight of a building that will be constructed on the sand above the clay stratum. So there is a planning that there will be some construction. Okay, so this is the proposed building, and for that the center of the clay will experience an average increase in pressure of magnitude 115 kilonewton per meter square. So delta sigma prime, if we denote this increase in pressure at the center of the clay, so this should be 115 kilonewton per meter square. So this is the problem statement. Now we have to calculate the expected settlement of the structure. Now, as you know that this expected settlement of the structure, so it would be due to the primary consolidation settlement of the clay, as well as truly speaking immediate settlement of the sand. But in this problem, since the data which are required for calculating the immediate settlement of sand is not provided or given, so we'll be restraining ourselves only for the calculation of primary consolidation settlement of the clay. Okay, so the main objective for this problem is to calculate the primary consolidation settlement of the clay. So this is the main objective. Now, how we can calculate this primary consolidation settlement of the clay? So we can calculate from this formula, that is AC equals to CC divided by 1 plus E0 multiplied by H multiplied by log of sigma 0 prime plus delta sigma prime divided by sigma 0 prime. And this equation will only be valid for normally consolidated clay, and it's explicitly mentioned in the problem statement that the clay which we are currently dealing with or in our hand, that is in the category of normally consolidated. So if the clay is not normally consolidated, rather it falls in the category of over consolidated, so in that case this formula or the analytical expression for calculating the primary consolidation settlement will be different. That we'll see in the subsequent problems. Okay, now we'll have to first understand what are these parameters involved in this equation: CC, E0, H, sigma 0 prime, and delta sigma prime. So first of all, this CC, this is the compression index. Okay, so we'll go one by one. So this is the compression index. Now, what is the physical significance of this compression index? So compression index is basically defined by the gradient of lower linear portion in the E log sigma plot. So this is the pressure void ratio versus pressure plot. This is a semi logarithmic plot because E is the arithmetic, the normal arithmetic scale, and sigma prime is plotted in the logarithmic scale. So that's why it's called semi logarithmic plot. Now in this plot, if you observe the trend, that is the variation of void ratio with respect to the effective stress, and that is the main observation for consolidation test, any kind of consolidation test, then you will be seeing that two segments are there. The first segment, which is having a very flat slope, followed by a linear segment which is having a steeper gradient. Now gradient of this second linear part, this is defined as CC. So CC, if you can see, so CC, it will be obviously delta E divided by log of, so if you suppose consider a change in, suppose this is your delta E due to the change in pressure delta sigma, so then it will be log of delta E by delta E divided by log of delta sigma, or rather we can say if it is sigma 1 prime and this is sigma 2 prime, then it will be sigma 2 prime divided by sigma 1 prime, where delta E, so this is suppose your E2 and this is your E1, so E2 minus E1, so this will be basically your E2 sorry, I am doing a mistake here because this E2 here, as you can see, as your space is basically increasing, so your void ratio is decreasing. So this will be U1 corresponding to sigma 1 stress, and corresponding to sigma 2 prime effective stress, the void ratio would be E2. So this will be U1 minus E2. Okay, so the gradient is negative, or rather here we can write U1 minus E2. Okay, so this is the definition of compression index. However, this kind of data is not available, at least for this problem. So therefore, the compression index, we have to, for the calculation of compression index, we have to take the help of some empirical relationship. And if you go through the literature, then you will be ending up with several relationships. And among these, this is one, 0.009 WL minus 10. So this is one of such empirical relationships available in the literature for the calculation of compression index. Okay, now this is for CC. Next, coming to your E0. E0 is the initial void ratio. This is before the primary consolidation. So this is the initial void ratio. So how we can calculate this initial void ratio? It's very simple because we know WGS equals to AC, and the soil mass is under complete saturation. So therefore, this A's value would become 1. So E would be W times GS. Okay. So we know the natural moisture content of the clay. We know the specific gravity of the solid particle. So therefore, we'll be able to calculate the initial void ratio of the clay. Next, coming to H, capital H. So this is the thickness of the clay layer. So this is the thickness of the clay layer. And this is, we can easily say that this is 18 minus 10, that is 8 meter. The clay layer is 8 meter thick. Okay. Then coming to sigma 0 prime. So this is the initial effective overburden pressure. Initial effective overburden pressure before consolidation. And lastly, delta sigma prime, this is the average pressure in K, average increase in pressure at the center of the clay stratum. So average increase in the pressure at the center of the clay stratum. So this is our first problem. So that's why I am discussing elaborately, little elaborately, all the terms which are involved in the calculation of primary concentration settlement. So next problem onwards will be simply writing down the value of this parameter and we'll be calculating. Okay, so we'll not spend much time at least for this part. So therefore, as you can see, the compression index you can calculate from the liquid limit of the clay stratum. You can calculate the initial void ratio from this relationship. You know the thickness of the clay layer. You know the delta sigma prime, that is the average increase in the pressure at the center of the clay stratum. But for sigma 0 prime, which is the initial effective overburden pressure, you have to go for some calculation. What type of calculation? That we'll see. So first of all, you have to know the unit weights of the individual stratum which you are having. So for example, this is a 2-layered soil. So the top layer is sand of thickness 10 meter and the bottom layer is clay of thickness 8 meter. Now further, this sand layer, which is having a total thickness of 10 meter, out of this 10 meter, the initial 7 meter is basically in the what we can say that it is above the groundwater table. That means we have to use the bulk unit weight, whereas 3 meter, the remaining 3 meter is under the groundwater table. That means we have to use the submerged unit weight for the calculation of initial effective overburden pressure. So initial effective overburden pressure, if we try to calculate, so this is simply the product or multiplication of the effective unit weight multiplied by the corresponding thickness of the soil. Okay, up to the part where we intend to calculate the effective overburden pressure. Suppose for consolidation problem, we would have to calculate the effective overburden pressure at the center of this stratum for which we are trying to calculate the primary consolidation. So therefore, obviously, the effective overburden pressure would be from the ground surface up to the mid depth of the clay strata. Okay, so I hope it's clear. So therefore, you should know the unit weights of this layer, sand and clay. Now for clay, since it's completely submerged, so its unit weight will use the submerged unit weight. But for sand, so it's partly submerged and partly under above water table. So therefore, we need to use two different unit weights when or while we'll be calculating the effective overburden pressure at the mid depth of the clay strata. Okay. Now coming to the unit weight. So for sand, two different types of units weights are explicitly or directly mentioned in the problem. However, for the clay, it's not given. So therefore, we need to go for some calculation for to determine the unit weight of the clay. And this unit weight would be submerged unit weight. Okay. So here I am rewriting the unit weights of the sand. So for sand, so we are having gamma bulk 17 kilonewton per meter cube. So this is valid from 0 to -7 meter. Okay, or let me write it in this fashion. Then gamma prime, this is 9.5 kilonewton per meter cube. This is valid for -7 meter to -10 meter. And coming to clay, we need to calculate the submerged unit weight, and it would be GS minus 1 plus E gamma W, if you can remember. Okay, so this would be valid for -10 meter to -18 meter. Okay, now what is the value of GS for clay? So this is 2.62. So this is this is 2.65 minus 1 divided by 1 plus E. Now what is the value of E? So this is simply W times GS, and the water content of the clay is 30.5%. Yeah, 30.5%, and the GS value is 2.65. So therefore 0.305 into 2.65 is 0.8083. 0.8083. Okay, multiplied by 10, that is for unit weight of water. So 2.65 minus 1 divided by 1.8083 multiplied by 10, it's 9.12. I hope 9.12 kilometer per meter. So in this way, we are having the unit weights for sand and clay respectively. Now we'll be calculating the effective overburden pressure at the center of the clay. Okay, at the mid depth of the clay strata. So sigma 0 prime, this is mid of clay. So this will be first the 7 meter portion multiplied by 17. 17 multiplied by 7 plus remaining 3, that will be multiplied by 9.5. So this is for our sand under or below water table. The first term for sand above water table, the second term is for sand below water table, and the third term, this is for the half thickness of the clay that is also below water table. So 9.12 multiplied by 4. So it would be 183.98. 183.98 kilonewton per meter square. So for this problem, we are calculating, or we have calculated the initial effective overburden pressure in a very straightforward fashion. However, you can calculate it from the very fundamentals. That is, you can first calculate the total stress at that point, then you can calculate the pore water pressure at that point, and you can subtract the pore water pressure from the total stress to evaluate the effective stress at that point. Okay, so that's little bit time consuming. Even though you follow that approach, you should be ending up with the same result, whatever or whichever we are getting from this by calculating the effective pressure by this fashion. Okay. Okay, so now I hope all the parameters, the values of parameters are with us. Okay, except this CC. So CC will be calculating here. It would be 0.00935 minus 10. Okay, so 0.009 into 25, that is 0.225. Okay, so E0 value already we have calculated. So it's 0.8083. So this is 0.8083, and thickness of the layer is 8 meter. Okay, and then the initial effective overburden pressure, just now we have calculated it, and it's 183.98 kPa, 183.98 kilopascal or kilonewton per meter square, and the effective or average stress increase at the center of the clay stratum is 115. This is 115 kilonewton per meter square. Now we'll substitute these values in the equation of SC. So SC would be 0.225 divided by 1 plus 0.8083. Yeah. Then multiplied by 8 multiplied by log of sigma 0 prime is your 183.98 plus 115 divided by 183.9. So if we calculate, so this would be approximately 0.210 meter, or we can say 210 millimeter. Okay, so this is the answer. So as you can see, just you have to remember this expression for the calculation of primary consolidation settlement. Okay, so I have mentioned this consolidation twice, so please correct it. In addition to that, you have to remember physical significance of all the parameters which are involved in this equation and the calculation procedure for each and individual parameter. Okay, so This is for this problem 1. Now we'll move further and we'll take our next problem. So in this problem again, the soil profile at a site for a proposed office building consists of a layer of fine sand 8.4 meter thick above a layer of soft normally consolidated clay of 2.5 meter thick. Now below the soft clay is a deposit of coarse sand and the groundwater table was observed at 2.4 meter below the ground level. The void ratio of the sand is 0.67 and the water content of the clay is 34%. The building will impose a vertical stress increase of 145 kPa at the middle of the clay layer. Now estimate the approximate primary consolidation settlement of the clay, and for that you can assume the soil above the water table to be saturated and compression index is for the clay is 0.33 and the specific gravity of soil solids is 2.67. So it's a very similar kind of problem to problem 1, except a few things, that is if we first draw the soil stratigraphy here. So it's a fine sand of 8.4 meter thick. So this is 0. This is minus 8.4. And then minus 10.9. That means 2.5 meter thick clay. And then again coarse sand. So this is fine sand, this is clay, and this is coarse sand. Okay. Now the water table for this problem is located at a depth of 2.4 meter below the ground level. So here, suppose. So this is the GWT. Okay. This is minus 2.4 meter. Now coming to the properties of sand and clay. So first of all, the void ratio of sand is given as 0.67 and the water content of the clay is given as 34%. The stress increase at the center of the clay, so delta sigma prime is given as 145 kPa. And in addition to this, the Cesi value for clay is given as 0.33 and the GS value is given as 2.67. Now we need to calculate the SC. Okay. Okay. Now what are the differences between problem 1 and problem 2? So in case of problem 1, the CC value was not directly given, but in this problem it's directly given. Where further in problem 1, the unit weights of sand were given directly. So in this case, this is not given directly. So rather the void ratio of the sand given. So from that you can easily calculate the unit weight of the sand. Okay. Okay. So please be careful about this statement also, that assume the soil above the water table to be saturated. So unlike the previous problem, so in this problem, this portion you have to be considered as saturated. Okay. Okay, now this would be submerged. Now what we need to calculate? We first need to calculate the saturated unit weight of the fine sand, then submerged unit weight of the fine sand, and submerged unit weight of the clay that would be required for the calculation of initial effective wall bottom pressure at the mid depth of the clay layer. Okay, so all other things you can easily calculate, because this SC, this is CC divided by 1 plus A0 H log of sigma 0 prime delta sigma prime divided by sigma 0 prime. And again, please note this terminology, that the clay in this problem is again normally consolidated in nature. Okay, now for this problem, the CC value is given as 0.33. Then E0 we can calculate from this relationship, as we have seen in the previous problem, W times GS, and W value is given as, I hope, 34%. So 34, so 0.34 multiplied by 2.67. So it's 0.9078. Then H, the value of H is 2.5 meter, that is 10.9 minus 8.4. Then sigma 0 prime, that we have to calculate, and delta sigma prime, this is 145 kPa. Okay, now sigma 0 prime, for the calculation of sigma 0 prime, we have to first calculate the unit weight separately. So sand, so gamma sat, so this would be GS plus C divided by 1 plus C gamma W, and it would be valid from 0 to minus 2.4 meter. Okay, so up to the groundwater table. Then 2.4 to minus 8.4. So for that, okay, first let me calculate the saturated unit weight of the sand. Okay, so one more thing, that this GS, this is not clearly mentioned, so it's either it's given for clay or sand. So therefore we'll use this GS for both the soils, so for sand as well as for clay. So 2.67 plus E. Now we have to be very careful for this E. So we have to use the void ratio of the sand only, not the void ratio of clay, since we are calculating the saturated unit weight of sand. So 0.67 divided by 1 plus 0.67 multiplied by 10, and it would be 20 kilonewton per meter cube. For submerged unit weight, so it would be GS minus 1 by 1 plus C. So either you can calculate in this fashion, or gamma sat minus gamma W. So since we have already calculated gamma sat, so it will be easier for us to calculate in this fashion. So it will be 20 minus 10, that is 10 kilonewton per meter cube. Now coming to clay, so your gamma prime, so this would be GS minus 1 by 1 plus E, comma W, and it would be valid for, okay, so here let me write the validity part. So GS is your 2.67. Now this E would be the E of clay, that is 0.9078 multiplied by 10. So that is 1.67 divided by 1.9078, 8.75 kilonewton per meter cube. So therefore, you can calculate the sigma 0 prime. So the initial 2.4 meter, it will be multiplied by 20. Then the remaining 6 meter, it will be multiplied by 10. And finally, the 1.25 meter will be multiplied by 8.75. Why 1.25? Because we are calculating at the mid depth of the clay strata. Okay. So 118.94. So this is the initial effective overburden pressure. Okay. So here we can write 118.94 kP. So therefore, the SC value, this would be 0.33 divided by 1 plus 0.9078 into 2.5 into log of 118.94 plus 145 divided by 118.94. So it's 0.150 meter, that is 150 mm. So this is the answer. Okay. So it's a very similar problem to problem 1, except a few cases. That is, in the first problem, sand unit weights were provided directly, but this is not the case for this problem. Then in the first problem, the CC value we had to calculate, but here it's rather given directly. So apart from these two differences, everything is very similar. Okay. So I hope so far everything is fine from your end. Now we can move further to take our problem 3, and it's related to problem 2. So we have to basically assume the same soil stratigraphy as given in problem 2, but now the clay is over consolidated with an OCR value 2.0, and the moisture content of the clay is given as 26%, CC is same 0.33, and the CS value, that you know that the CS represents the soiling index, so its value is given as 0.045. So all other soil values remain unchanged. So we need to determine the primary consolidation supplement of the clay. So we'll see what would be the change due to the over consolidation. Okay. Now a few things that we need to recalculate for example, the submerged unit weight of the clay, we need to recalculate, because earlier the water content of the clay was 34%, but in this problem the water content of the clay is changed to 26%. So therefore we need to recalculate the submerged unit weight of the clay. Okay, so only for clay, not for sand, because it's mentioned that all other soil values remain unchanged, okay, except the parameters which are given to this problem. So clay, your gamma prime would be gs minus 1 divided by 1 plus c, and what would be the value of e? E would be wgs. W value is given as 0.26. gs you can take it as 2.67. So 0.69. Okay, so this is the E, or initial void ratio you can say, multiplied by gamma W. So GS is your 2.67 minus 1 divided by 1 plus 0.6942 multiplied by 10. So this would be 9 point, I hope it's 9.86 kilometer per meter cube. Okay. Okay. Now, for this problem, since the soil is basically over consolidated now with an OCR, so the primary job is to calculate the maximum past effective overburden pressure, which is defined as the pre-consolidation pressure. So pre-consolidation pressure you need to calculate first. So how you can calculate the pre-consolidation pressure? How you can calculate? So you can calculate this pre-consolidation pressure if we denote it by sigma c prime from the OCR value. Now OCR, this is nothing but over consolidation ratio. Now what is over consolidation ratio? So over consolidation ratio is defined as the ratio of the past maximum effective overburden pressure to the present effective overburden pressure. So this is called OCR. So if you know the OCR value and if you know the present effective overburden stress, then you can easily calculate the pre-consolidation pressure from this relationship. So therefore, as it is quite obvious that we need to calculate the sigma 0 prime first, then we need to multiply this sigma 0 prime with the OCR, given OCR value, to get the, or to obtain the pre-consolidation pressure. So we'll do that. So first we'll calculate the sigma 0 prime. Sigma 0 prime, for the calculation will follow the same procedure that we have followed in the last two problems. So the initial 2.4 meter sand, it will be saturated unit weight. In the next 6 meter sand, it will be submerged unit weight. And for the half thickness of the clay, so I will use a separate color here, it will be different. So a 9.86, so it will be 9.86 multiplied by 1. So it's 120.33 kPa. Okay. Now we have calculated the sigma 0 prime. So sigma c prime, this would be OCR multiplied by sigma 0 prime, and the OCR value is given as 2 multiplied by 120.33. That means 240.66 kPa. Okay. Okay, so 240.66. Now we have to go for a check. So what kind of check? So we have right now three stresses, that is sigma 0 prime, sigma c prime, and sigma 0 prime delta sigma prime. Okay, we have to check the chronology of or order of these stresses. So whether sigma c prime is greater than sigma 0 prime or not, and it's less than sigma 0 prime plus delta sigma prime or not. Okay, so why it's important, that we'll see. So as you can see that sigma 0 prime, this is 120.33 kPa. Okay, and sigma c prime is your 240.66 kPa. So obviously sigma 0 prime is less than sigma c prime. Now we'll check whether this value is less than sigma c prime or greater than. So it's 120.33 plus 145, that is 265.33. So sigma c prime is less than sigma 0 prime plus delta sigma prime. Now accordingly we have to modify the primary consolidation settlement equation as we have mentioned in the very beginning. So the equation which we have used for the previous two problems, that was valid only for the normally consolidated clay, but since the soil is over consolidated clay, so we have to modify the equation a little bit. Okay, so we have to calculate in two steps. So the first step is from sigma 0 prime to sigma c prime, and the next step is sigma c prime to sigma 0 prime plus delta sigma prime. So for these two stress increase, two different stress increase, we have to calculate it separately, and then we have to add these two components to get the final primary consolidation settlement. Okay, now for this stress increase sigma 0 prime to sigma c prime, we have to use the swelling index, that is CS, and for sigma c prime to sigma 0 prime plus delta sigma prime, we have to use the compression index. Okay, so in this range it will be, we have means over consolidated clay, and it will as if anormally consolidated. So our modified equation, so it will be CS by 1 plus E0 H log of sigma c prime divided by sigma 0 prime, that is the over consolidation ratio, plus Cc divided by 1 plus E0 H log of sigma 0 prime plus delta sigma prime by sigma c prime. Okay, so in this way there may be different cases possible, different combinations can be possible. Okay, so it may also be possible that this increased stress, the total stress after increment, it is less than sigma c prime. Okay, then it will be only utilize the swelling index, so that you can see from other example problems as well. Okay, right now, so this is the chronology. So you have to basically utilize CS and CC separately. So for sigma 0 prime to sigma c prime, you have to use CS swelling index, and from sigma c prime to sigma 0 prime plus delta sigma prime, you have to use CC. Okay, okay, so now we'll substitute these values. So your CS value is given as 0.045, 0.045 divided by 1 plus E0. Now E0 for this problem is 0.6942 multiplied by 2.5 multiplied by log of 2, that is over concentration ratio, or rather we can write 240.66 divided by 120.33. Okay, so this is for the first part. Then coming to the second part, so it's 0.33 divided by 1 plus 0.6942 multiplied by 2.5 multiplied by log of 120.33 plus 145 divided by 120.33. Okay. So we'll calculate it separately. So first of all, for the first part, so it's approximately 0.020. Okay, so this is your SC. Now for the second component, so it's 0. Okay, sorry. Here it's sigma C prime, that is 240.66. 0.021, therefore 0.041, or we can say 41. This is the answer. Okay, so in this way we can calculate the primary concentration settlement for an over concentrated clay. So just you have to be very careful about this chronology of sigma 0 prime, sigma C prime, and sigma 0 prime plus delta sigma prime. So accordingly you have to modify the consolidation settlement equation. Okay, the equation for the calculation of primary consolidation settlement. So this is the only thing that for that you need to be very careful. Otherwise means all other things, the remaining portions are exactly similar to the case of normally considered clay. Okay, so now we'll take this problem 4, and it's regarding a consolidation test. So during a consolidation test, a sample of fully saturated clay 2.5 centimeter thick is consolidated under a pressure increment of 180 kilonewton per meter square. When equilibrium is reached, the sample thickness is reduced to 2.15 centimeter. The pressure is then removed and the sample is allowed to expand and absorb water. The final thickness is observed as 2.3 centimeter and the final moisture content is determined as 21.8%. If the specific gravity of the soil solids is 2.67, find the void ratio of the sample before consolidation. Okay, so this is an example of consolidation test. So how the data are basically observed or recorded, so that you can basically witness from this problem statement. Now if you read the problem statement very carefully, then you can realize that three specific conditions are mentioned in this problem. Now, what are these three conditions, or three, rather than we can say three stages, are explicitly mentioned for an consolidation test in this problem. Now, what are those stages? The first one is before consolidation, the second one is after consolidation when the equilibrium is reached, and the final one is when the unloading is basically happened. That means the pressure is removed and the sample is allowed to expand and absorb water. So three cases are basically talked about in this problem. So before consolidation, after consolidation, and after unloading. So these are the three cases. Now corresponding to these three cases, we know the thickness. Okay, so in some cases reduced thickness, in some cases the soil thickness, and for one case we know the void ratio, and that is only for the, or only at the end of unloading case. Now what we have to calculate? We have to calculate the void ratio before the consolidation. Okay, so that we'll see how we can calculate the void ratio of the sample before consolidation. Okay, so now if we draw a schematic of this test, suppose this is the sample, or not schematic, so if we basically write it in a tabular form, so this is the stage, we can say. So one is before consolidation, the second one is after consolidation when equilibrium is reached, and the third one is after unloading. Okay, so these are the three stages. Now what is about the thickness of the layer? Sorry, a thickness of the soil sample and void ratio. Okay, this is your H and this is your E. Now before consolidation the sample was 2.5 centimeter thick. So this was the thickness, 2.5 centimeter. Now when it is consolidated under a pressure increment of 180 kilonewton per meter square and the equilibrium is reached, the sample thickness is reduced to 2.15 centimeter. So this is the new thickness after consolidation. Then the pressure is removed and the sample is allowed to expand and absorb water. And as a result of that, the final thickness is observed as 2.3. So initially, due to consolidation, the thickness is basically reduced. Reduced by what amount? 2.5 minus 2.15, that is 0.35 centimeter. Then when again the pressure is removed and the sample is allowed to expand and absorb water, the thickness is increased and increased to a value of 2.3 centimeter only. So it's not increased to the original value. Okay, so the settlement which is basically occurred in the sample that is not exactly regained or removed due to the unloading operation. Okay, so some amine supplement basically happen. Now, what is about the void ratio values? Okay, so void ratio values for this stage means before consolidation we have to calculate. That is the main objective of this problem. However, if we read the final two sentences of the statement, that is the final moisture content is determined as 21.8% and the specific gravity of soil solids is 2.67. So anyhow, we can calculate the void ratio corresponding to after unloading phase. Okay, so how? Because since the sample is completely saturated, so we can calculate the void ratio from this expression, W times GS, and W, this is given as 21.8% and the GS value is given as 2.67. So therefore, we can easily calculate the void ratio after unloading as 0.218 into 2.67. So which is 0.5821. Okay. So 0.58. Now what we'll do, we'll basically proceed in the backward direction. Okay. So in the backward direction, we'll basically proceed to calculate the void ratio for the remaining two stages, that is after consolidation and before consolidation. How? That we'll see. Okay. So that we'll basically do by this process which is called change of void ratio method. Okay. So change of void ratio. So you can go through the lecture content, then you can come across this method. So as per this method, the change in void ratio can be expressed in this fashion, that is delta E, delta H by H equals to, or rather we can say H naught equals to delta E by E naught. Okay, so this is the expression where delta is, this is the change in thickness, H naught, this is the original thickness or the reference thickness with respect to, we are basically calculating the change. Then delta E, this is the change in void ratio, and E0, again this is the reference void ratio. Now since we are basically proceeding in a backward direction, so 0.5821, so this is our reference void ratio and this is our reference thickness for the first step, 2.3 centimeter. Okay, so step 1, this is in between stage 3 and stage 2. Now here your delta E divided by 1 plus E0, the E0 value, that will be 0.5821. So 0.5821 would be equals to delta H by H naught. Now what is the change between these two stages? That is 2.3 minus 2.15. So 2. Sorry, 2.3 minus 2.15, and this is 2.15. Okay, so therefore from this equation we can calculate the delta E value as 0.15 divided by 2.15 into 1.5821. So 0.1104. Now This delta E, if we denote this void ratio as E1, E2 and E3, then this is E3 minus E2. Okay, so this is E3 minus E2. So this is 0.1104. So obviously your E2 value would be E3 minus 0.1104, and E3 already we have calculated as 0.5821. Okay, the suffix denotes the stage, so 0.5821 minus 0.1104. So that means 0.4717. Okay, let me check it once whether I did a mistake or not. So 0.218 into 2.67, so this is 0.5821. Now 2.3 minus 2.15 divided by 2. Okay, so here I did a mistake because the reference thickness here is 2.3, not 2.15. So this would be 2.3. Okay, so please correct it. Into 1.5821, so that is 0.10, 0.1032, 1032, 1032. So 0.1032. So 0.5821 minus 0.1032. So it's 0.4789. 0.4789. So this is after consolidation, but we need to calculate the void ratio before consolidation. So therefore we have to again go for another step, step 2. Okay, and this would be in between stage 2 and stage 1. So in this case the reference values will be corresponding to stage 2. So therefore 0 delta E divided by 0.4789, this would be 2.15 minus so this was the thickness corresponding to after consolidation, and this was the thickness corresponding to before consolidation. So 2.5 divided by 2.5, or delta E equals to minus, so it will be 2.15 minus 2.5 divided by 2.15 multiplied by 1.4789. So it's minus 0.2408. 0.2408. Our delta E is basically E2 minus E1. E1, it should be E2 plus 0.2408. So 0.4789 so that means it's 0.7197. 0.97, and this is the So if we write it in this box, so first of all, this value is basically 0.4789, and then this value we have got 0.7197, and this is the answer. Okay, so this is the way to calculate the void ratio corresponding to each stage of the consolidation test. So this is one method, change of void ratio. There is another method, change of height, I think. So you can also go for this approach, but ultimately you will be having the same result. Okay. So this is for problem 4. Now we will take problem 5, and this is uh, taken from GATE examination 2021. Now in this problem, the soil profile at a construction site is shown in the figure, and this figure is not to the scale. Groundwater table is at 5 meters below the ground level at present, and old well data shows that groundwater table was as low as 10 meters below the ground level in the past. Take unit weight of water 9.81 kilonewton per meter cube, and the over consolidation ratio at the midpoint of the clay layer is. So in this problem, basically you have to calculate the over consolidation ratio. So right now we are familiar with this over consolidation ratio because we came across this term in problem 3, and this is nothing but a ratio of, so if we write it here, so it would be, sorry, so it would be the OCR, it's the ratio of maximum past effective overburden pressure the soil had faced the present past effective pressure. Okay, and the sigma c prime is nothing but pre-consolidation pressure and this is the present effective pressure. Okay, now as you can see from this problem statement, two scenarios are mentioned in this problem. So first of all, presently the water table, groundwater table is at a depth of 5 meters. So this is the present scenario. However, an old well data shows that the groundwater table was as low as 10 meter below the groundwater. Okay, so below the ground surface. So suppose something here. So this is the past, this is the past groundwater table location. Okay, so this is your GW2. Now, due to this lowering of this groundwater table, there might be some increase in the effective overburden pressure at the center of the clay, because we need to calculate the OCR at the midpoint of the clay. So therefore, the main task to this problem or of this problem only to determine the present effective overburden pressure at the midpoint of the clay and the past effective overburden pressure at the midpoint of the clay, and then take a ratio of these two effective overburden pressures to obtain the over consolidation ratio. Okay, so that will do. So first we'll calculate the present effective overburden stress. So for this, okay, so as you can see, there is no need to calculate the unit weights because the unit weights are directly given to this problem. So for sand, above the groundwater table, the unit weight is given as 17.5 kilonewton per meter cube. Then below the groundwater table, the saturated unit weight of sand is given as 18.5 kilonewton per meter cube. Therefore, the submerged unit weight gamma prime, it would be 18.5 minus 9.81. So in the earlier problems, we have assumed the unit weight of water or considered the unit weight of water as 9.81 kilonewton per meter, is 10 kilonewton per meter cube, since it was not mentioned explicitly. However, in this problem, it's clearly mentioned, so therefore, we need to consider this value only. So 18.5 minus 9.81, so it's 8.69 kilonewton per meter cube. Okay, so this is for sand. Now for clay, the saturated unit weight is given as 17 kilonewton per meter cube. So therefore, your submerged unit weight would be 17 minus 9.81, that is 7.19 kilonewton per meter cube. Okay, so this is for clay, and we need to calculate the over consolidation ratio at the midpoint of the clay. So for present scenario, the sigma 0 prime at point A, suppose we have chosen a point here, this is A. Okay, so this would be first the sand portion above water table, that is 17.5 into 5 plus below water table portion, that is 8.69 into 15 minus 5. Okay, so the total thickness is 15. So 8.69 multiplied by 15 minus 5 plus the clay portion, that is 7.19 multiplied by 4. 7.19 multiplied by 4. Okay, so if we calculate 17.5 into 5, 8.69 into 10 plus 7.19 into 4, so it's 203.16 kilonewton per meter square. Now coming to the past scenario, okay, so coming to the past scenario, your sigma c prime at A, it would be 17.5 multiplied by 10. Why 10? Because in the past, the groundwater table was located at a depth of 10 meter. So 17.5 multiplied by 10. So therefore, the remaining sand portion was 15 minus 10, that is 5. So 8.69 multiplied by 15 minus 10. And the remaining clay portion is unchanged. So if we calculate, then it would be 247.21 kilonewton per meter square. Now we'll have to take a ratio of these two values. So OCR, it would be past by present, as I mentioned earlier. So therefore 247.21 divided by 203.16. So it's approximately 1.22. The value is approximately 1.22. This is the okay. So it's a very simple and straightforward problem. Just you have to calculate the two effective stresses, one in the past and one at present, and then you have to take a ratio of these two values to obtain the over consideration ratio. And you have to be very careful when you will be going for the calculation about the location where you need to calculate the over consolidation ratio. So for this problem, it's required at the midpoint of the clay layer. So is it okay? So already we have solved a few problems regarding various aspects of primary constellation settlement. So how to calculate the primary constellation settlement for normally consolidated clay, over consolidated clay, and then the calculation of over consolidation pressure, and one problem regarding the calculation of void ratios corresponding different stages of consolidation. For example, before consolidation, after consolidation, and after unloading. Means it's consolidation. So for different stages, like after loading, before loading, after loading, and after unloading. So you can put in this way as well. Okay. Okay. So if it is all fine from your end, then we can take our last problem for this session. So this is also again asked in GATE examination. This was asked in GATE examination 2021. So in an odometer apparatus, a specimen of fully saturated clay has been consolidated under a vertical pressure of 50 kilonewton per meter square and is presently at equilibrium. The effective stress and pore water pressure immediately on increasing the vertical stress to 150 kilonewton per meter square respectively are. Okay, so this is a very fundamental problem. For that, you need to answer a few things. For example, when we consolidate a sample, what are the variations in the total stress, effective stress, and the pore water pressure with time? So this is the main concern of this problem. So if you know the variations of all these three pressures with time, then you can easily address this question. Okay. So I am discussing a little bit about this variation. So for example, when t equals to 0, so if you try to draw the variation with depth, that is z, okay, so this is your total stress. So it's suppose a constant value. Now coming to the pore water pressure, so it can be basically inferred or interpreted from the spring cylinder analogy or spring dashpot. Okay, the spring analogy that we have basically mentioned at the beginning of this session. So when the load is immediately applied and the water behaves as an incompressible material, so the all the pressure which is basically applied will be taken care of by the water only, pore water only. So therefore there is no stress transfer happening to the soil particles, particle to particle contact immediately after applying the load. So therefore all the pressures which are applied, that will be solely taken care of by the pore water, and that's why the excess pore water pressure will be equal to the total stress. Okay, so this is your z and this is your pore water pressure. So obviously your uh, effective stress will be simply 0. This is the effective stress. So this will be simply 0. Okay, no value. This is again Z. Now time frame for a time which is in between 0 and infinity. So what will happen? The total stress remain constant. The total stress remain constant. So if we denote it as sigma, so sigma, this is u, this is sigma prime. However, due to the permeability of soil, so what will happen? The excess pore water pressure, which is basically generated due to the application of load, that starts to dissipate. Okay, and it dissipates very quickly at the edges as compared to at the center. Okay, so this is something, the variation of u versus z. Now coming to the effective stress, therefore as you can see, so something this kind of variation you will get. Okay. Now t tends to infinity. With due course of time, what will happen? So all the stresses remain constant, total stresses, so it will not change. However, the pore pressure now becomes zero. So all the excess pore water pressure dissipated. Okay, at infinite time. So therefore, now all the total stresses is converted to the effective stresses, or transferred to effective. Now, if you observe very carefully for this problem, this condition is mainly discussed about. Okay, that is immediately on increasing the vertical stress. So if you apply the vertical stress or increase the vertical stress, so immediately after increasing, what is the condition? What are the effective stress and pore water pressure? Now, what is the increment? So earlier the vertical pressure was 50 kPa. Now it's increased to a value of 150 kPa. So that's why the delta sigma prime value is 150 minus 50, that is 100 kPa. Now immediately after increasing this vertical stress, this 100 kPa will be solely taken care of by the pore water pressure. Okay, nothing by the contact, soil to soil contact. Okay, so therefore your u would be, the pore water pressure would be 100 kPa. However, your sigma prime value, this would be 0. Okay, so this is immediately on increasing the vertical stress. Okay, so this is also a very simple question. Just you have to brush up the fundamental things. Okay, so if you forgot, so just you need to know the variation of this total stress, pore water pressure, and effective stress with depth throughout the soil sample with due course of time. So how it will vary. Okay, so starting from p equals to 0 to infinite time. Now we'll take one homework problem before concluding this session. So in this homework problem, it's given as, after a laboratory compression test, a cylindrical specimen of saturated clay was found to have a mass of 175.82 gram and thickness of 18.77 mm. After drying to a constant weight, its mass was 130.28 gram. What is the void ratio at the start of the test when thickness was 19.6 mm if the diameter remains constant and the sample remains saturated? Assume the specific gravity of soil solids is 2.67. Okay, so this is a very similar problem to problem number 4, I hope. Yeah. So this is a very simple problem, a similar problem to problem number 4, because in problem number 4, there are also this kind of data, but in a more direct way it was given. So for example, uh, two stages that are talked about. So one is before consolidation, and then after consolidation. So first of all, thickness, and then void ratio. Okay. Now before consolidation, the void ratio was 19.6 mm, and after consolidation the thickness becomes 18.7 mm. Now void ratio you have to calculate before consolidation, means at the start of the test, where the void ratio after consolidation is somehow known. How it's known? So it's basically known. Now how it's known? That is the main trick here. So it's known from this relationship W times GS. The GS value is 2.67 here. So this GS value is 2.67, and water content that you have to be determined from the given data. Now what is water content? Water content is nothing but the ratio of mass of water to mass of solids. Okay, so mass of water to mass of soil solids. Now as you can see, this is basically nothing but the data regarding water content determination, that a cylindrical specimen of saturated clay was found to have a mass of 175.85 gram and thickness 18.7. Now after drying to a constant weight, its mass was 130.28 gram. That means this mass is nothing but your mass of solids, and this is nothing but your mass of solids plus mass of water. So two masses are basically mentioned here. So one is 175.82 gram, this is before oven drying, and M2, this is 130.28 gram, this is after oven drying. Now a difference between these two masses, or rather we can say M1, a subtraction of M2 from M1, that will represent nothing but the mass of water. Mass of water is your M1 minus M2, and your mass of solids is nothing but M2. So you can easily calculate the E value from this equation. W times GS, W you can calculate from this ratio, MW by MS, GS is given. So this void ratio value is known. Now once it's known, how can you calculate the void ratio at the beginning of the test? So again, you can use this method, that is the change of void ratio. It is delta E divided by 1 plus E0 equals to delta H by H0. So the reference void ratio and thickness, you can take it at after the test, and then you can calculate the change in the void ratio, and from that change you can easily calculate the void ratio at the start of the test. So this is the thing that already we have done or followed for problem number 4. Okay, so nothing means what I can say, nothing more than this problem 4. Okay, so exactly the same thing which we have done in problem 4, that has to be repeated for this problem. Okay, so I am not solving this problem further, so it's your homework. So I'll request all of you, so please attempt this problem, please try to solve this problem, and let me know if you face any difficulties while solving this problem in the next session. Okay, so this is all for today's session. So now I will be waiting for a few minutes for any clarification or doubts that you have. So you can unmute yourself and you can ask me. Okay, so for your kind information, so we'll again meet on next Sunday, that is on 17th March at 5 p.m. So okay, so thanks for joining this session and have a nice day ahead. So let me know if you have any doubts, okay? At least for this session, the problems which we have solved for this session.